hard.
Okay, so we're in. Lab 8 and 9, we're really just lab 8, I guess, and main memory management. So choosing a location for a new process. So this is review. This is like a review of what we did.
Yeah.
Remember that there are in the method of continuous allocation, right? Because when you have a new process, you got to give it memory.
Yeah.
So we have to choose a location for that memory. We can do continuous. Continuous here it says. Should be contiguous really.
Yeah.
Whatever. Continuous is also good because it continues. It continues all together. The point is contiguous and it's one block. So but you're gonna have holes in main memory. Continuous or contiguous allocation of entire process. Variable allocation of memory chunks. In other words, the chunks that are given are variable size. That's what we mean by that. The lecture teaches different methods for selecting the hole in which a new process entering the system will be inserted. We have best fit, worst fit, first. We really just did best fit, worst fit, and first fit. There's also a next first fit. The truth is, what we mean by next first fit is like this. How do you decide what's the first fit? Is it from the beginning of all the memory, or is it from wherever you last left off? And you were going to take a pointer to the memory holes. You have a list of all the holes, and you have a pointer at the beginning of the list. And as you go through, you find one. Now you need another one for a different process. Do you continue from where you left off, or do you go back to the beginning? So that's the difference between first fit and next first fit. First fit means the first fit from going back to the beginning every time. Going back to the beginning of the list, first fit every time to the beginning.
Next.
And the next first fit means you pick up where you left off. That's all. So we have one more system now. We learned now another way. I mean, of course, that could be a test question. I don't have to teach it to you. You can still figure out what next first fit means. But I mean, you have to be explained. You have to be but then you have to understand the right question. Memory allocation and paging. Given an operating system that has been proposed to use contiguous, here it's written right, allocation of segments. It was decided that allocation would always be in multiples of 2 kilobytes. Did we do this example? No. The system's internal memory size is 128 kilobytes. So therefore there's 64 possible units, right? But what does it mean that allocations would always be in, okay. Please share your thoughts on this method, its advantages and disadvantages. For the answer to this, consider internal fragmentation, efficiency of memory management, the need to store information about small holes. So what do you guys say? We have, it doesn't really give you much information here. It's not such a complicated system by any means. Allocations would be in 2 kilobytes. The system, so that just means, well, I mean, it means that let's say I need 6 kilobytes, so we'll give me 6 kilobytes. If I need 7 kilobytes, we'll give me 8 kilobytes. If we have okay, I mean that's about it. So what do you say? So you
For internal fragmentation, there's going to be a lot of this.
Right, there's going to be an average internal fragmentation of half of 2k, which is 1k.
Is it half of 2k? It's like half of the size that's stored. Like,
no, it's half of 2k.
No, but if you store, so if you're trying,
if I'm storing 7, then I have DACA 1k.
But if you're storing 9, then there's
also 1k.
7k. In multiples of 2k, not.
Yeah, let's say you're storing 9 and a half.
Not powers of 2k, multiple.
Yeah, I think multiples is just times 1 times 2 times 3.
Okay, fine. Yeah, then average of 1k.
So the average internal fragmentation will be 1k. Efficiency of memory management. Well, it's kind of efficient because we won't have to deal with well, actually not. We'll have holes still because we're in contiguous.
Yeah.
We're still gonna have
holes the size 2 kilobytes.
We're gonna still have all kinds of holes. The smallest hole will be 2 kilobytes.
Yeah.
The biggest.
But no,
The biggest hole could be
the biggest hole will be the whole computer.
Oh, yeah, right.
The smallest one will be 2 kilobytes. So the need to store information about small holes. Well, so I think what they're saying there is that like the most we would want to have to store, we'll never have more than, let's say, 63, holes, and then there was, what's the maximum number of holes? So you'd have to have 30 something holes.
Yeah.
You can never have more than. Like, you know.
Yeah, you
if
can
you
have
had every other one, that would be the worst case, so then it would be 30,
pseudo I guess. Maybe 31.
maybe 32 holes, yeah, 32, maybe 33, I don't know, 32
Some of
holes. You basically have 32 holes, not more than that. Let's see, oh, we don't have an answer.
Also,
That's-
so they need to store information that's small, but.
What?
It doesn't matter.
No, that's what I mean, they need to store information about small holes, I'm saying,
Yeah,
we'll have to store up to 32 pieces of information about these
so
holes.
this is also like pretty bad for the other reason, because like if you have 64 very small processes. Like they each, that they take up whatever, 10 bytes.
You could only couldn't have 65, right,
You
that's
could-
another thing, the maximum number, we could say that, another thing we could say about it, the maximum number of processes on such a machine is 64.
Yeah.
Even though there's, some of them might be very small. Continuation of the question, memory allocation, in light of all the data, in other words, assuming that we're still in this world of 2 kilobyte allocations. What are the memory status at the time 114? So let me stop the share for a second,
Um,
and then. Because, well, you're on the cell, but what's the memory? You can't really see it anyway, probably, the viewers at home probably can't see this anyway, so I may as well do the share. Share. Okay, so. What do we do?
Are they all connected to this?
High floating meeting controls.
Ooh.
And now it's gonna give you that shading screen forever.
No.
I think they should change the amount of seconds. it's on.
Yes.
Yeah,
Those are always on Twitch.
Okay, so what are we writing here? This is a little, yeah, so we have exit time. Arrival time, wait,
Arrivals have
I mean,
exit.
shouldn't know what is the memory status? What are they?
in light of the data, what is the memory status? In other words, where are their holes and everything?
Yeah.
So we're saying like, so process. Zikaro, wait, I think this might be the answer.
No.
Think about this, wait a second. Exit time. Arrival time, the arrival time, we're gonna start with arrival time, so we see,
They want us to fill in the last line.
it could be that they wanted to fill in something here, but let's see. The arrival time is at, doesn't matter, we'll figure it out in either case.
Yeah.
The arrival time is at 100 and it leaves at 105.
Yeah.
And this one comes a little bit later at 103 and then leaves at 108. And then, oh, but before he left, this one came at 107. Okay,
A lot of processes coming in.
this process coming in and going out. Process capacity, which means how much they need, how much they require.
In kilobytes, system.
Assume it's in kilobytes here. And process number.
Yeah.
And zikaron, so. Well, this doesn't match up, does it? It's got a little bit pushed down.
I think it's, I don't know, because that was P2.
This must be for,
I don't understand. I don't see.
oh, this might be the answer.
No, hang on.
No, P2. Is already gone by 14. By 14, who's still around? Only P1. And P19. And P4. P4 and P1 are still around at.
But it's asking for like which holes are in the,
Yeah,
were created by that. So,
well, wait a second. 0 to 6K. His capacity,
who came first?
One.
Who came first?
this doesn't make any sense, right?
Maybe this is like a wrong. I
I don't know what that answer is.
Maybe
Okay,
it's
let's
that
figure it
one?
out ourselves. Let's figure it out. This is actual test question. It was actually a test question. I remember this. I remember this exam and I was like, I remember like thinking, why does he give me such an exam? I mean, not to, you know, just to grade it, you know, just to.
Are you given answers? Do you have to find answers yourself?
What?
Are you given answers or do you have to solve it yourself?
No, I don't think that I got answers here. All right, so wait. I guess we can stop the share. We went through the diagram. Let's stop the share, maybe somebody who wants to see me.
And Whoever's at
Oh,
home, they
it's
can open
safe.
up the slide for themselves.
Whoever's at home, you can take a screenshot now and
Yeah,
then,
take a screenshot now.
and then look at what we're doing on the board.
Stop the share.
Or just download.
Somebody should have like, there's like campaigns, stop the steal. We can have stop the share. Isn't it stop the
There
steal?
was, yeah,
I don't know, exactly who was it?
that's like a Trump thing. the election.
Stop the
Use
sale
like
on the
election like
sale.
Oh, but now I got this thing on here. How do I get rid of this? Minimize that, okay.
Ooh,
I mean. You guys
So-
don't see the board.
So let's just do it because this is
Let's see
the,
the board. Wait,
What?
oh, they don't see the board. Do they see the board?
I think the board is really small now. Like,
Oh, yeah, no, we have to switch it.
no, they see this.
Will the recording show that?
There's no share. So they just see this
So
thing,
if it's not sharing, why is it? Ah,
because I minimized it.
okay, fine, yeah.
I don't know how it works then.
I know. how it works.
Yeah, okay, I really trust you.
Okay, so let's start like this. At time. Where are we?
So at time.
At
zero.
time 100.
No, wait,
Why does it start off?
Because it's just the other guy, I don't know. I know this guy who writes this, he just gets things into his head. But what does it matter? Sometimes people like to make the test more complicated, just like instead of thinking about a creative question, they just make the numbers like funny, so then it's like.
Let's start at like arrival time 1274.
Yeah, just to make it confusing. Okay, so at 100, what happened?
He takes the first 20.
You
P
take
zero
20.
takes 20, the first 20 kills.
First
So
20
let's
of
draw a
the-
picture of the
Take
memory.
first 32 kills.
Here, let's draw a picture of the memory, and this is gonna be easy to draw, because we're gonna write like 0 to 2 to 4.
We're gonna need a lot more. It's like, it goes up to 100.
Wait, does it? Wait.
What?
It goes up to, I don't know, how much did it say go up to 128? So, like, I
It
don't
does
think.
64.
Well, okay, I'm drawing as fast as I
No, it goes to
can.
128, I think.
Wait,
Let's draw the numbers closer together.
It's in bigger. No, we don't have to draw every single number.
2, 4, 6, 8. Okay, you're saying just, that's the idea though. I'll just draw some of them, 10, 12, 16,
Why don't you just put?
et cetera, et cetera, et
Hang on.
cetera, until,
Why don't?
how much is it?
Put multiples of
Wait,
eight.
hang on.
120
No,
no,
don't do that.
128.
When you're thinking of
128.
it, put its entrance and its exit number.
Oh, that's actually a good idea.
That's what we will do, so we'll do, okay, but you got the idea, so you got the idea, 2, 4, et cetera, until 128.
Yes.
So one comes along and he
Goes
and he
up to
wants
From
20,
0 to 20.
his capacity is 20, so he's
Take
from
from-
0, well, that's an interesting question, it's from 0 to 20, fine. This is also the question, is it 0 to 20 or 0 to 19? Well,
0 to 19.
019 is probably right.
it's 0,
It says process capacity is 20, then we go from 0 to 19.
well,
We did-
this
we
is
did-
19 and 20, this is the line where 19 ends and 20 begins.
Yes.
So 20, the next one would be 20.
Yeah, I guess, okay, I think he did the question wrong though. Okay, it's whatever.
So.
No, you can get it wrong that way if you didn't do it right.
Next
It's-
next one
it's
arrives
exactly not
at
that.
103.
What?
Next one arrives at 103.
Next one
Okay.
arrives
103 takes 5.
at 103 and he's still there, right?
Yeah.
So,
He takes 5.
so wait, this is P, let's write his number, wait, you didn't, help me out, this is P what?
P's
P
zero.
P zero.
Now P1 takes up
P1 takes
to.
5, so.
P1 takes
P2,
24.
P2.
P2 comes at 103,
It takes 20 to 24. It takes 20, 24.
and this is 23, and it's,
Twenty-
now
I
it's
think it takes 24,
24.
24 because.
Cause it takes.
Yeah,
5
yeah, but-
spots.
20,
It takes
21,
five spots.
22,
It takes
23.
It takes 6 spots
24.
actually. It's 25.
5 spots.
It's 25.
Wait,
Takes
how much
five-
does it take?
5 slots. so
You
it's
guys are
25.
messing me around.
Sorry.
Capacity is 5,
It
that means it's
24.
6, so what are you talking about?
Yeah.
It's 26, and this is 25.
Yeah,
No,
there we go.
No, that's 6 spots.
Why
No,
He's
20,
Round it to
20,
2.
21, 22, 23, 24.
It's multiples of
25.
2. It's
That's
multiples of
6.
2.
Yeah, 8 wants 5, not 6.
Multiples of
Yeah,
five,
but we have multiples
multiples
of 2.
Multiples of
Oh,
2.
wait,
Remember, that was
Yeah.
our prerequisite.
Ah.
Remember the
so-
previous thing. So this is P, this is P what?
P2.
And let's do like this. Let's mark off internal fragmentation. Just for the sake of internal, just for the sake of noting it to ourselves. That's
Alright,
internal fragmentation, not external fragmentation.
alright.
Now,
Now it's P3.
let's get rid of this line here.
P3 comes at 104, and yeah, no one's finished yet. So P3,
P,
104 and it's-
104, nobody's finished yet.
P4 gets
So P3, when this P3 comes?
Yeah,
P4.
P4, you
Well,
sure?
P3, sorry, I'm sorry, P3.
I thought it was P3
I'm
also.
sorry, you're right, it's P3. He gets
P3?
70.
70, so now you gotta do a little hard math here.
95.
What's 70 plus
95.
26? 90, what?
95. 95.
Up to 95, which means
96.
96 is here, and this is P3.
And no internal problem.
No.
And what?
No
fragmentation.
And no fragmentation.
Perfect.
And
Now,
now
people finish. Oh,
Now
P0
P0
finishes.
is finished.
P0 finishes.
P0 is finished, so you just mark them off.
Yep.
Okay, and now what
So
happens?
now P5 comes in.
P5 comes in, right?
What time is it?
107.
107.
P5.
P5 comes in and he needs 25.
25. So
And oh, that's the whole point, you can't go here.
Yeah,
No,
oh,
you
no.
can't. So
But wait, which algorithm are we doing?
The one which was
I think
decided
that's first
before,
fit.
it was,
First
Um,
fit next, actually.
Oh, is it
oh
first?
yeah,
fit?
it says
I
first
see the word
fit.
next there.
Is it first fit next? First fit.
First fit, which one? Well,
Oh, I see, first
Okay.
fit next.
Does it say here?
No,
Okay.
you're going, you went down.
It doesn't say, okay,
It will say here, but it says first fit next.
But that answer's already wrong.
but in any case, it doesn't matter because even if it's first fit or first fit next, we're still gonna go
Still
here.
gonna go here.
Yeah,
First
so-
fit.
So how many is it?
96, makes it one.
How much is the total amount?
26.
25.
It's 25,
Four
let's add a little fragmentation here,
Oh, sorry, 120.
and it's 26, 26.
122 and fragmentation.
122 in fragmentation, right? Yeah, 122 and 121 above and 122 go up.
121 is here and 122 is there.
Yeah.
Okay,
And
and this is,
now-
what's his number?
This
P,
P5.
P5.
So
who is
now.
this, wait, let's see who this is, the dead guy here.
P2 ends.
Wait.
P0.
What is this,
P0.
P what?
0.
P0,
Okay, so now P2 ends.
okay, and now P2 ends, so let's
Yeah.
here,
P ends at
let's
108.
do. P2 ends, P2, just to know that they're finished,
And
okay,
you can delete the fragmentation line as well.
and now this fragment becomes bigger,
Yeah, you
Yeah.
can delete the fragmentation line.
and we can delete the fragmentation line.
Yeah.
Okay,
Just put the line back again.
It's a black.
no, you know there's a line there. You can
Yeah,
see it
we
up.
can see it.
Alright,
Okay.
so,
That was P.
So now-
So we don't
P1
do
comes
P4, what about P4, is it come along yet?
P2
you know, P1 comes in.
Oh, P1,
And
what time are we, what's the
We're
time?
at 108.
We're at 110 now.
We're at 108, we just moved to 110, which is. P1.
108 was who?
P2
Well,
finished.
P2 ending,
P2
ending.
ended, okay, and now we're at 110.
110, which is P1 entering,
P1 entering.
and that is 12. But
P1
you go
wants
down,
12.
which you go down, no, it can't.
Well, if it's next, we have to go here,
But it's
we
not,
can't,
not
enough
enough space.
not enough space, so anyway, we'll go here.
Yeah,
So now we go, so
Zero
it doesn't
to
matter
16.
whether it's
No.
next, so far it doesn't
No,
matter.
hang on, hang on.
0 to 11.
The 0 to 11,
So this is 11, and
And
we'll write
underneath-
12 there. And he
And-
needs 12?
yeah,
Okay.
so that is P1. Yeah,
That's
P1.
P1,
Yeah.
so we still haven't, I still haven't seen P4 for a while. Is there a
Okay, so-
P6?
no, hang on, so we're at
We-
1.
what's-
No, we only have one more,
Wait,
P4.
so P.
Oh, P0,
P0
P3,
finishes.
no, P3 ends.
P0 finished, P2 finished.
That's right, P3 finished.
Wait, I got 0, 1, 2,
P3
3.
just finished.
We need to do, what?
P3 just finished. At
P3
111.
just finished.
Yeah.
And now who's left? Still
So
P4 hasn't come?
Now P5 ends.
Wait, where does P3 finish? How do you know?
There,
P3
111.
111.
And now
111, and when does
P5
P,
ends.
I'm still waiting for P4.
P4 it comes
P4 comes in after, but P5 ends now at
P5
112.
P5 ends,
At
At
112. And then
P5
after that, P4 comes in.
so P5 ends also. So
Yeah.
who is this? This is who?
That was P4, right?
Yeah,
No,
P-
no, sorry, that was P1.
Yeah, no,
P3, I'm sorry.
P3 ended,
Yes.
and now P4, P5 ends.
P5,
So now.
and
the whole thing
now
is basically empty.
Yeah, no.
everything's empty and comes along.
Comes along P4 at 113.
In here
And
he wants
he needs
7.
7.
So
So
he goes
from
from
112 to
he goes
1.
from, see, no, he goes from normal 12.
112 to 119, which is 1.
Not 1, just
No,
12.
sorry,
12 to 19.
Yeah,
Sorry,
sorry,
12
Well, how
to-
much does he need?
He needs
Needs
7. He
Which
needs
means
7.
8, which means
Yeah.
8, so to 20, so it's
So
actually to here again.
Yeah,
Yes,
exactly.
it's
Wow.
P4
Convenience.
And also a,
and fragmentation.
Fragmentation.
and this is P,
P4.
and that's it.
But now, hang
Oh,
on.
which
It's a kind of a bad example.
We're at 113.
Now we're at 114. This is our
So
ending point.
at 115.
Well, we don't care about that, we're at 14.
114.
That's our answer.
114.
So this is, in my opinion, this is what happens when you just put random numbers and you just see and let the students figure it out. But because this actually is not a particularly interesting example, because nothing actually happened that was uncomfortable, for example, there was no, we just have everything together.
Yeah,
and
so
we-
it'd be
we
nice
go.
that one ends up there, one's over there. Instead of
Yeah, it would be
having
nice
to-
if you had, or if you had something that like had to skip or something, or you couldn't allocate it. So what is this line here? Talik Matzav. So he says that P2, P0, and P8 are still in memory.
There's no pH, what is he talking about?
Yeah, it doesn't make any sense. Okay, that just confused you.
So
No wonder
it's
people
saying
did,
it's
no wonder people did
an-
badly on the exam.
No,
Nobody, for some reason, nobody got that answer.
I mean, that says a dugma to us, it's not the actual answer.
You're right, I take it back, we like to make fun, you're right, I forgot that, I read it before. My memory is very bad, and even though I read this and I saw that it said that, this is like a dogma exactly, in other words, this is the way he wants you to write the answer, he's just saying, the answer should look like this. This is
Yes.
free, this is occupied, by who
If
is
it
it
would
occupied?
have been tshuva le dugma, then it should be the answer, but it's dugma le tshuva. So it's an example of the
Yeah,
answer.
Right, it's not, it's it would have been Chuva
I think the
Dugma,
next
yeah.
five are the answer.
Okay, answer.
ooh,
Apparently.
Memory apparently the answer depends on the algorithm chosen to use the
Well,
select.
Oh, do you think next one wanted you to do all of the types?
First fit, in the first fit in the list, that is the largest enough. Next fit, the first fit in the list from the point where we stopped, that is large enough. Best fit, smallest whole, worst fit.
we did the first two.
We did the first two, and we may have even done best fit too.
Oh, that's actually possible.
We probably did best fit, we didn't do worst fit.
We did not.
You got the basic idea. So here is this the same one?
Oh, here, walk through this.
Yes, it is.
Then, they're not gonna walk us through it. Okay,
They will.
It's the same.
so let's see,
I don't
solution,
remember what we did.
worst fit, best, so wait, we did first fit, is that, do we have that one?
I think we have P1, P4.
What do we have, what do we have? We have
P1 and 12,
P1
yeah.
and P4, don't we?
Why don't we pick P1? It's not P1. He's lying to us. He says P1 when it should be P0.
They're
No,
all
what
the
are you talking
exact-
about? Look here.
They're all the exact same.
Oh, that's the ending. That's the ending, yeah.
They're all the same.
You're just telling you the answer.
Yeah.
We got it, they're all exactly the same. Yeah, it's exactly, it's kind of a stupid example, did we?
Yeah.
0, but look what he wrote there. He wrote 0 to 12, and then 12 to 20.
That's because they're
That's a
on.
way of phrasing. Like it's an exclusive last thing.
Right,
Oh,
It's
but
it's the
yes.
way to 12, and then from 12 to 20, it's probably the right way to do it, actually.
Maybe.
I just think about it too much, I overthink it a little bit. But yeah, that's probably the right
I
way.
put you at 11.
I can
11
say
to
that. Makes
19.
sense to me. 0 to
No,
12,
yeah, that's
12 to
very-
20 seems like
what?
you're using 12 both times. Like it's kind of weird. I don't know why it counts for it.
No, until the 12 point, until the infinitely small 12 point. And then, that's the way, yeah, you're right. You're right. I remember when I say, what if a student writes 11? We don't know if he got it right or wrong, maybe he meant until 11. It's confusing, but yeah, no, but this is a good way to, actually, I think, this is a good way to do it. I think, the more I think about it, I've seen this example actually for several years. And if he would have written 11 and then he write 12 here, he might be indicating to me that he wants to say there's a gap. Although he would have written free, you should have written free there.
Hey, don't put free at the end of each one.
Anyway, yeah, they're all exactly
Oh,
the
wait.
same. I, by the way, went through this, I had to
Oh, yeah.
rearrange, move all these things around because of the translations. Got all screwed up. And it was
Oh.
stupid to do, because they're all the same. So anyway, it's a very stupid example because it doesn't show the point of there being different
Yeah,
algorithms.
I wanna see something.
But it doesn't matter, you guys can figure out the best fit also. It just means instead of choosing the next space, you choose the best place. Question,
Wasn't like the last class was just us two, also like a question heavy class?
what,
I don't remember.
what do you think?
I think the last class was just us two, it was also like very class heavy one, so we had to do the person first out, like the
Well,
CPU.
Yeah, there are a lot of. I think the slides from now on, like at the start, they were kind of teaching their own thing, but now there's like.
Well,
examples.
I have to tell you, wait, it's like,
Mhm.
you escape, why is my escape not working? There, where, I wanna go here.
We probably should
Here.
share.
I wanna share, exactly, share. Share. And share log. Okay, from current slide. Okay, so we just wanted to see, this is the answer, and for those people at home. Somehow don't have the slides, because, yeah. And this is the answer, we see that they're all, this is a beautiful example to show that there's no difference between the algorithms, if that was your goal. Okay, question, let's say there are 6 free sections, partitions of memory. Of the following sizes, so we have. The sizes are 125, 750, 200, 350, 600, 300. Describe the memory status for the following algorithms. First, best, and worst. For each algorithm, consider the situation where the allocated parts are, in order, allocating from right to left. So from right to left, this is also supposed to be from right to left. So from right to left, 300, in other words, we're actually starting over on the right
Oh, yeah.
and not on the left. It's a little bit confusing that way. And our first free space is 300, and our second free space is 600. So, and then we want to come in with 115. Where are we going to put it? Well, if it's first fit, we're going to put it here. If it's worst fit, we're going to put it here.
And if it's best.
And if
fit,
it's
we'll put it in
best
1.5.
fit, we're going to put it here.
Yeah.
So.
Yeah.
First fit, best fit, worst fit, here is our 300.
Mhm.
First fit should go. Oh, it went there,
Wow.
isn't that
That's
beautiful?
unprecedented.
And then we have leftover of 118, and then best fit, I hope he does this one next, no, he doesn't. He does all of first fit,
Oh,
okay, first fit, so that comes along.
Which one?
Wait.
No, this one's left to right. This time it's left to right. Now comes all the
Allocation
500.
request, why is this way, why are these numbers different?
These are left to right, I think.
What are the different numbers?
Are they different numbers? Oh, yeah, they are.
Oh, because this is the situation,
Yeah.
and these are the requests.
Yeah.
So 115, yeah, now they're left to right. 115, now comes 500, gonna go right there.
Not
And
gonna
it goes down,
358.
isn't that beautiful?
Yeah.
And then 380, well, it can't, 358 can't go here, can't go here, it goes here. I mean, this I could teach to 6th graders, I think. And then 200 goes, why does 200 go here? Because it's first fit, we go back to the beginning, you see.
Yeah.
Well, either way, we would have gone here. If we would have wrapped around, we would have come here also. Because 200 can't go there. Would have been more interesting if he had, like, let's say the number
380.
100. And then we would have gone here, or if he had the number 100, and no, we weren't, we had 150.
I think
If he had 150, we would have continued to this one, skipped it, and then gone there. I don't know, whatever, okay.
Ah.
Anyway, so 200 goes there, then the next number is 375,
can't go.
it can't go. Well, it can go,
Oh.
398,
Oh, there.
392.
Oh, yeah, there's space there. I didn't see that.
So there you go, and we're 17 left over.
Ooh.
That is first fit. Now let's do best fit.
115.
Ah, right, because we said that. Best fit, 115 should best go over here. Then 500 should go into 600, right? Because you can't, better than 750. And then 358 should go in this, the only place it can go.
Yeah.
And then 200 should go in the 200, obviously. And 375 should go nowhere.
No, 392.
No, go here, yeah. Go here. I would like to have a nowhere. Let's say worst fit. Okay, so that worked out. A little bit different. We ended, now let's see, let's compare it actually. Best fit
That's
gave
what-
us bigger holes, right?
No, on average, the holes are smaller.
No, best fit gave it 300 holes. There's no 300
Oh,
holes.
hole, yeah, holes, yeah, you're right.
Better holes. We have better holes than 350. We have
Ooh.
better holes. That's sort of better position. That makes sense.
No, which one is better holes?
Well, I'm saying. Well,
I think first,
best fit gives us bigger holes, I said. I didn't say better holes. Because you might argue that we avoided, by using first fit, we avoided having this 10 left over, which is probably gonna be useless for anyone. Because it's so small. And we have a 17.
for first fit,
Here, we just have 117.
for first fit, all of our holes are small. Yeah,
Yeah,
okay,
are smaller
yeah, that's better.
than the holes that we have here.
Okay, fine, I see.
Now, worst fit says put the 115 Dafka here.
Yeah.
And then the 500.
Also there,
Also there. And then the 358
in the 600,
can only go here. And then the 200
in the 350,
in the 350.
and now we're stuck.
And now we're stuck. 375. I knew they were stuck at something.
Yeah.
375 doesn't go anywhere. And Now the memory section has to wait. So worst fit, even though it's a counterintuitive idea, is also a wrong idea. Sometimes counterintuitive ideas are good ideas, but this is a counterintuitive idea, which is actually not so good. I don't know who thought of it. I like my algorithm. I should put on the exam a question like that. I haven't invented a new algorithm where the first one that comes in is best fit. The next one is worst fit. The next one is best fit. Then best fit, worst fit, best fit, worst fit. Well, just see what happens. See if it's good. Maybe it's good. Maybe it's good. Cut your losses. Try both. It's like, you can't decide on chocolate or vanilla, get them both.
But also alternate between first fit. Like every third one is first fit.
Yeah, I consider every third one is first fit.
And every fourth one is last fit.
Oh, last fit. Well, that fit is just, it's pointless. There's no difference between last fit and first fit. It's where you started from. Okay, page tables. That was that. Now we go to page tables. Question, access time. Given a memory, this question I wrote and rewrote a couple of times. I'm saying this week I changed the slides. So you'll have to tell me if you agree with it. Given a memory, as the other ones I didn't change. This one I'm changing because this is my pet topic. This whole thing with pages. Given a memory system with a cache access time of 10 nanoseconds. Nanoseconds are big or small?
Small.
Are they very small?
Very small.
Like,
Because I need more for first
What, billions of?
What is the size of a nanosecond? Small.
I'll tell
very
you, I
small?
have to say, I really do realize that I write hard exams. Because I just saw the exam for a different course and software engineering.
Yeah.
And it's so, in my opinion, the questions are just like that, like. Which is bigger, a nanosecond or a microsecond?
We had most of our exams been hard. We had like one exam, which was like the intro to data security, which is like so trivial. You could have skipped every single class, not known the topic, and I got 100.
Yeah, I'm not gonna do that. I don't do that. My goal is to punish those people who didn't come.
Actually reminds me, my brother was in university.
Of course, they watch the video, then I can have to.
My brother was in university in Toronto and one of the professors had a motorcycle and he liked to talk about it in class. So one of the bonus questions at the end of the exam was, what kind of motorcycle do I have for extra like 5% or something?
Yeah, there you go. 5% is smarter than 5 points. Because then
Yeah.
you reward people who did well more than you reward people who didn't do well.
Yeah, it's like, if you're in class, you'd know.
Right. Well, that's what professors do in universities, actually. That is standard. That's kind of standard thing to do. Professors have, but on the other hand, it's like illegitimate. I never understand, I told you this, I never understand how come like, this professor got into trouble for saying that the Palestine, that I don't know, or whatever, he's saying that Israel was right to take over the West Bank or whatever. I don't understand what was his course in modern and contemporary politics. That's the name of the course. No, he's a professor of chemistry, or he's a professor, never a professor of chemistry. It's usually a professor of like some social science, of like sociology or history. But why would a professor of sociology? He's got a textbook of sociology. What is he talking about? Whether Israel should have invaded
Yeah, so
Gaza.
if he does talk about it, he's wasting.
And then the only reason they're upset about him is not because of that he said it, but of what he said. I don't understand why I with that, but anyway,
I'd be upset.
I do it too, I guess, but I try to avoid it. I talk about my personal life, but I don't talk about. I try to keep other topics out of this. The access time to the main memory is 110 nanoseconds. Oh, I got you. Yeah, okay. 110 nanoseconds. So wait, what's the difference?
Cache.
With a cache access time. Ooh, this sounds like data, like computer architecture. We have a cache and we have a main memory. Assumption. So the cache is more than 10 times faster than the main memory. Assumptions. The main memory access times includes the time to check whether there is a cache hit. So in other words, that's an all-inclusive number. Assumption. There is no reference to bringing the page into memory, only to the access time to the page table. I wrote that. Yeah, I wrote that. There's no reference. There is assumption. There is no reference. That's what I mean to say. We're not thinking about bringing in a page into memory. Only the time to access the page table. Is that right?
That makes sense. It's just access time there is no.
It is known that the effective access time is 10% greater than the cache access time. That is, whatever it is, the effective access time is 10% greater than the cache. So how much is the effective access time? It's 10% greater than the cache, so what is it? So we're given,
11
this is like a backwards question, we're given the
11
solution.
nanoseconds.
What?
11 nanoseconds?
Thank you, 11 nanoseconds, it's 10%, so the total average is 11. And the cache is 10, and the memory is 110. And we're not thinking about anything but just getting the memory, we're not thinking about, there's no reference to bringing the page into memory. That should really be the word page table, it should really be
What else?
accessing the actual memory. Anyway, what is the proportion denoted by H of cache hits? What is the proportion denoted by H of cache hits out of total memory accesses? In other words, how often do we get a hit and how often do we get a miss? It's really a question from
Yeah.
computer architecture.
Yeah,
Answer. I don't know what this is doing here, but the answer.
effective access time.
Yeah, that was, we proved that kind of thing. I never understood where this two comes from, but
Okay, what is that?
that's an equation that you're supposed to know. The EAT equals 2 plus E minus alpha. Remember what E is? E is the time, it's irrelevant in this case, but alpha is the hit, hit rate, and epsilon is the time
Oh, yeah.
to bring it in.
To bring in new stuff,
Yeah.
No, it's not the memory, it's the
storage.
it's the hit, it's the time to get to the TLB. It's the TLB time. Anyway, first we calculate the effective access rate.
What's
10% greater, so it's 11 nanoseconds, like you said.
Mhm.
So we already figured out now the AAT is 11. Overall, the effective access time is calculated relatively. The fraction of time that will change after hit times 10, and the fraction of time that will change after hit, and the fraction of time that there is a miss.
8 times 10 nanoseconds?
So I don't quite, I might have been writing this pretty late at night. But the point is like this, 11 has to equal
Yeah,
the hit rate when it's a cache, the whatever the rate of time
yeah,
that it's in the cache, plus whatever rate, when it's not in the cache, it's gonna cost me 110. Notice, it was given to me that whatever is not in cache, it's 110. We're not thinking about, there's no reference to bringing the page into memory. It should really be only access time to the page table, and it really should be the page itself, not the page table. In other words, we're actually getting the page.
yeah. Yeah. Makes sense.
It's a confusing question. It's a confusing question because what we really need is when there's a cache hit and a memory read, it takes 10 nanoseconds. As a cache hit combined with the memory read, because we're ignoring the memory read, the actual memory read. This is just the cache. And this is just saying that we're reading, in other words, we're ignoring the memory read itself. This cache, it's the effective access rate to the page table, not the effective access rate to the actual memory that I'm interested in.
Okay, yeah.
That's what it is.
Oh.
It's the effective access rate to the page table, and the memory is something else. We're just interested in active. So, okay. So.
Yeah.
So we just calculate that. H times 10 plus 110 times H. So it goes to 10H plus 110 minus 110H. So that means that we have 100, we take minus 10, we take the minus 100 and add it to the plus 10, and we get minus 100. And we get 11 equals minus 100H plus 110.
Mhm.
So we subtract the, whatever, you just move everything around, subtract the 11 from 110, and you get 99. And the 100H you put on the other side and make it into a plus. You take the negative 100H, put on the other side, you get 100H equals 99, or H equals 99 divided by 100, or 0.99. So what does that mean? That the hit rate is 99%. Okay, that's it. But again, really I should remember to change this to access time of the page table, that's what it is. Okay. Reminder, how many bits are needed for each memory size in bytes? So this is just, okay, reminder, you should all know this by heart,
Yes.
right? We've discussed this a million times. Is this clear to you?
What is this?
One, if I have, if the maximum size access, in other words, if I have only one bit, I can only access 2 bytes of memory.
Mhm.
2 bytes of memory with 1 bit. Either the first byte or the 0th byte. If I have 2 bits, then I can get 4 bytes. If I have 11 bits, then I can get 2048 bytes. I can reference each
Kilobytes.
one.
Yep.
That's gonna be relevant to
Two,
this.
no, 2 kilobytes.
Questions? Calculating the page,
The bytes. It's bytes. No.
calculating the page table. There is a machine with 8 gigabytes of memory. The size of each page is 8 kilobytes.
Right.
That's actually nice numbers.
Mhm.
So how many, by just offhand, how many,
1,000.
no,
8 megabytes?
Sorry, a million.
1 megabyte.
it's a million, approximately a million. Right, it's really 2 to the 20th, which is
A megabyte.
a mega. There's a mega, not a byte, but
A
a
mega
mega page. There's a machine with 8 gigabytes of memory, the size of each page is 8 kilobytes,
There's one
so there's a
mega
mega page, it's got mega pages.
So
But
one
it's really
megapage.
2 to the 20th pages,
Yes, 1 megapage.
which is a little bit more than a million pages. Each row in the page table is 4 bytes in size. The logical address space contains 46-bit addresses. So that's 46 bits is actually able to reference more than 8 gigabytes. How many bits do you need to reference 8 gigabytes? 33.
Bits?
33.
33. That makes sense.
33, makes sense. 2 to the 30th
Is
is a gigabyte. And we have 8 more, so 8 is 2 to the 3rd, so it's 33.
Megabytes or megabit?
We're not talking about megabits in this course, ever. I denote a megabyte by a big B. And a megabit would be with a little b.
Yeah, I know, but
And these are big B's. The truth is, these are all wrong notations. It should be G little I B
Yeah,
and K little I B.
yeah,
Yeah.
that's the correct.
Because because otherwise this could be understood
Rate
as an actual 8, as an actual 8 million. Or 8 billion. Round not 10 to the 9th. Okay, the page table must be paged into page size units. And therefore, the outermost page cannot be larger than 1 page. You understand that? We want the page table to be in page size units. There's no memory in our. Remember that the outermost page has to be contiguous.
Yeah.
Right? The outermost page has to be contiguous, and the page table must be paged into page size units. Therefore, the outermost page has to fit into a page. It has to be, can't be bigger than 8 kilobytes. How many levels of hierarchical paging will we need to map the memory? You understand the point? If we have a picture, let's see the picture. Do I have a picture? Yeah. In other words, like this. If this is my page, let's say this is a page. Of course, this is just an example. This is a page, and this is a page, this is a page, and all this together are my entire page table. Then how many levels do I need? Here it's showing 2 levels, because why? Because this one references 4.
Mhm.
So he gets 1, 2, 3, 4. And this one references the next 4, and this one the next 4, and this one the last 4. And this one references 4,
Mhm.
so he can reference these 4. Works perfectly. If I would have had one more page over here. You understand, you guys, are you with me?
I'm really not focused.
You're not focusing? Well, I have, this is a community thing. Look at this is a very nice picture. This is my page table. My page table has in it information about where pages are on the computer. How many rows is in my example, we said that how many rows does my page table have to have? Approximately 1 million.
Yeah.
Approximately 1 million rows. This page table is a simpler example. This page table has how many? 4. This is each of these are a row, let's say. Oh, each of these, yeah.
84.
4 times 1, 2, 3, 64. 4 times 4 is 64. 64, there's 64 rows here, right? In order to access all the 64 rows, if each of these contains 4, I divide 64 by 4. And what do I get?
60.
So I need 16 pointers to point to these. There's 16 of these boxes here. So I need 16 pointers. So how do I get 16 pointers? I divide 16 by 4. And what do I get? 4. So I have 4 groups here. Each one with 4 pointers. 4 times 4 is 16. I have 16 pointers. And now I have 4 groups here. And I want to have 4 pointers pointed to them. And now I can get anywhere I want by starting off at the top. My hierarchy gets me everywhere. My question is now, what if I had one more, if my memory space allowed me one more exactly, one more page,
You know, so.
then I'd have to have, then these are not enough. I'd have to have a whole nother level.
Yeah.
I'd have to add a level over here with 4 pointers, and only one of them would point to this, and one of them would point to
Another set of 4.
another one like this.
Yeah.
And he would only have 1 pointer pointing to that one. I'd have to make the whole level bigger, because I might have to always be balanced. My tree has to always be balanced.
A lot of wasted overhead.
Yeah, well, it's not really, there's only 1 extra piece. It's not so much, it's like 3 pages. So when we take, yeah, so fine, let's just understand it like that. So wait a second. So if we have 3 levels, then how do I identify? Well, first of all, to identify the offsets here are this is a pointer to a page, right? This guy is a pointer to some page. So that's the offset. The page size. This is how many bits. In this example, this guy is pointing to a page of what size? This blue one here at the end is pointing to a page of what size?
Which one? Oh,
Anyone, well, but I'm pointing to this one, what page size is he pointing to? What's the size pages in our scheme here?
Each
This diagram.
8 kilobytes?
what color?
In this diagram.
No, in this diagram, this is a different example.
Oh, this is a different example?
How can we know?
You can know, because this,
It has 4.
let's say a row is 1 byte.
Size of 1.
You're right, it's 4 rows, we don't know how big a row is. But,
Just 1.
so our offset is gonna have 2 bits for those 4 bytes.
Yeah.
The offset for this guy is gonna point to a page, so this is 2 bits, and then this one is gonna be the mapping to find which. Assuming I've gotten this far, let's say I've come to this guy, but I have to know which one to point to, because in here, this is like the offset, this number here is the offset within here. And this number here, middle row, is the offset within here. And this global one is the offset in here, which is this, it's 0, 1, or 2, 0, 1, 2, or 3. Because this number will be 0, 1, 2, or 3. This number will be 0, 1, 2, or 3. This number will be 0, 1, 2, or 3, and this number will be 0, 1, 2, 3. So the address is 2 bits plus 2 bits plus 2 bits plus 2 bits. 2 times 4 is 8. 8-bit address. That's this example. Is that what they did here? Or they did 6 somehow. Whatever. Oh, here, they're gonna show you. This is telling me to go here.
Yeah.
Then the next 2 bits, it's like I said,
Yeah.
this is telling me this is the middle one. This is telling me to go here, because it's 2.
Yeah.
So if I got this address, I would know immediately where to go. I would go to here, because this is 3, 0, 1, 2, 3, 3. And then here, 2 tells me go
This third one.
on this one.
To the third one. It's not, it went into circle.
It's a little bit not, they didn't show
The
the
third,
third, there,
third.
third one, and there it is, okay, there's the third one. So that's what it's telling me, but I just added, that's these 3 left boxes. The 4th box, I added in, which is, once I'm actually there, now I have to look at this offset to know, well, this guy's pointing to a page, what part of that page? Okay, so now, back to our question, that was a reminder, see it says reminder? So back to the question, what was the question again, do we remember what the question was? I got it. Here's the question. 8 gigabytes of memory, 64-bit address, 8 kilobyte pages. How many rows do we need to have so that it'll work? So, I'm gonna do this in a very simple way. You guys are with me? You're all playing with your computers.
No, I'm just fine as well, it's easier to see it.
First, we calculate the offset we need. How many bits are needed to address each byte within the 8 kilobyte page? It is necessary to reach a single byte out of 8,192 bytes,
13.
right? Because it's an 8 kilobyte byte, so we will need log 2 of that number, which is 13.
13.
Basically, it's just saying
8.
2 to the 13th power is 8 kilobytes.
Yeah, 8 you can address it.
In other words, this is the size of our page, which is 8,192 bytes. We need a bit. How many bits do we need? So you just do log 2 of that number, and you get the answer. 13. Out of 46 bits of logical space, we have 33 left over for the row of the table. Right, each row, because remember, we don't gonna store the offset in the row, we're just gonna store the row. Now, it happens to be that 33 bits fits into 4 bytes. We calculate how many pages of memory one page table can reference. Each row in the table is 4 bytes. How come it's 4 bytes? Notice I read a big B. 4 bytes. Why is it 4 bytes?
4 bytes would be 32 bits.
Yes, why? Oh. No, oh,
That's 33. 0 to 31.
oh, you're right. In order to. You're right, how does it 4 bytes enough?
I think it's meant to be 45 bits and 13 is used and you have 32 left. Maybe it's supposed to be 46 bits and we use 13 and we have 32 left.
Yeah, that's a problem. I don't know why I must have been writing this late at night. 4 bytes is only 32 bits. How can I fit? Alright, let's imagine that somehow we could squeeze in 34 bits into 32 bits. Why is this not a problem? It's just be a problem.
I mean. That's just like a little bit ahead and the bottom thing says 2 to the power of 11 times 2 to the power of 11 times. I'm like,
Yeah, well, let me get,
11,
go ahead.
22.
Why would you go ahead?
so it's gonna be 11, 22, 33. But what did it do to the
No,
11?
it says 33. It says 33 bits plus ability meaning. Wait.
Oh, plus the validity bit. But no, but yeah.
Each row
33 is
in the
equal-
table is 4 bits in size.
Also the entry, but you have to include one as the
No.
validity bit, which is not part of the entry.
I don't know.
What?
So you have the 32 of
You
the
don't need-
entry plus 1 of the validity, then you have the 13 of the address. So.
You don't need to have the address. What's 13?
That's right,
The 13 of the offset, you mean?
that's right, the 13 on,
You
yeah,
don't
no,
put the
no,
offset
you have
in the
46.
page there.
No, the 46 is 13 of the offset, 1 validity and 32 of the entry. Maybe?
Okay, let's just continue with the way I said it. Imagine that somehow it fits into 4 bytes. And then we'll have to rework this question. But 4 bytes in size, in order to fit 33 bits, fine. Let's imagine that 4 bits is enough. You're right, we need 8. We need 8 bytes.
No, I'm saying maybe the validity bit is not included in the 4 bytes.
Doesn't matter. It's 33 doesn't fit into 32.
Yeah.
33 is bigger than 32.
Yeah, I know, but
So it
I'm
doesn't
trying
work
to say
out.
that. The 33
4 bytes
is-
cannot store 33 bits. Plus a validity bit would be 34 bits. We already calculated 33 bits because we need 33 bits to identify the page.
I'm saying that-
Because we have 13 taken off. This won't work.
No, I'm saying that the validity
No, we need.
is part of the 33 and we.
No, but it's
then we
not.
exclude- It's not.
It's not, that's what I heard you, and I'm answering you, that's not true. Because we calculated the 33 over here as by taking 46 and subtracting 13 from it.
Yeah.
Oh.
I thought that would be.
Oh, yeah, my mistake. Wait, it's 46 minus
Yeah,
So
I
13.
thought the
We
46.
have to change it from 46 bits to 40, from 46 to 43. That'll be fine.
Hey, I thought the 46 was including the.
Okay, I carry your
And
thought.
the.
I don't care what you thought. Doesn't say that.
Huh?
Doesn't matter what you thought. Okay, so this is wrong, but let's just leave it and imagine that it worked. I should go back and change it from 46. Change this number from 46 to,
45.
no,
44.
44. It has to be 44. 44 minus 13 will be
41.
31.
31.
And 31 plus 1 is 32. It fits exactly into 4 bytes.
Alright.
We should change this to 44. Because we're 2 bits over. So imagine that this is 44. I'll change that. Now, each page in the page table should have a page size of 8 kilobytes, because we said everything is 8 kilobytes. We divide the page size by the entry size. What's the entry size? The entry size we just said is 2 bytes. It's 4 bytes. So we get 2K or 2048 entries per page. You understand why? Because 2048 times 4 is what? 8,192. So that if each row is 4, then we have 2K. Notice we have 2,048 entries per page. If we assume, I'm just going to assume the answer. This is the way I did it. I decided to do it like backwards kind of. I'm saying let's assume we know the answer. Let's guess the answer. It's either 3 or 4 or 5, right? You just try. Let's guess. Let's guess that it's 3. Let's assume that we need 3 levels. That would mean that we could access, if we had 3 levels, how many could we access? How much could we access? Well, we would have 2048 at the first level. And then each of those 2048 each one would point to 2048.
Yeah.
So that's 2048 times 2048. And if we had a third level, then each one of those could point to 2048. So it becomes 2048 to the third. But the final one that we have is also pointing to, has an offset of 8K.
Yeah.
Because we got the page, we now know where the page is. But in the page, there's 4 kilobytes. So how much memory is that? How much is 2048 to the third times the offset? Well, if we multiply it out, it's 2000. It's 2048 is what? It's 2 to the 11th. So it's 2 to the 11th times 2 to the 11th times 2 to the 11th. And then the last one, why did I write 2 to the 13th?
8 kilobytes.
8 kilobytes is 2 to the 13th. And if you multiply this all out, you add the exponents and you get 2 to the 46. And we get it all.
So.
Actually, this is a problem though, because why? Because if I change it to 42,
44.
sorry, if I change it to 44,
Then we can't access all of them.
then we'll have more.
We need 4 levels.
No. Why 4 levels?
Because then we will only have. Oh yeah, no, you're right, we'll have more.
We'll have more.
We'll have more than enough, which is fine. Why is that an issue?
We'll have more than enough.
That's
Which
fine.
is fine.
Yeah.
What is the maximum virtual memory space that can be given to a process? 2 to the 48, that size. 2 to the, in other words, that whole number of bits. It's always gonna be like that. It's always gonna be whatever they told us. 40. Look, what's 2 to the it's gonna be 2 to the 46. That's what was given. We're given a lot. It's a stupid question because look, it says we have a 46-bit logical space. So obviously, the amount of virtual memory that can be given is 46 bits, which is 2 to the 46, or 220. I mean, it's not a stupid question. It's just emphasizing the point. It's that number that we got.
Yeah.
2048 to the third times this kilobytes. Oh, that should be a big B.
Yeah.
I gotta edit this later.
Okay, and big B.
What? Should be a big B.
Also in the line, in the other line as well,
Yeah.
Oh, wait, where are we? Right,
a little bit,
there, okay. This should be a
Also-
big B.
yeah, and also a little bit above
Here,
there, that'd be.
yeah. Basically, yeah, whenever I am confused in one thing. Whenever I refer to bits, I write it out.
Yeah.
I write bits, C-B-I-T-S. Okay, next question. Writing and reading to disk, given a system that performs, I wanna finish at 8. What time is it? 20
It
minutes.
is 7:36.
Writing and reading to, what time are we supposed to finish?
7:50.
Oh, 7:50, so I'll 7:50, okay. Writing and reading to disk, given a system that performs compaction. Remember that compaction? That you, if you have a lot of fragmentation
Oh,
and
yeah.
you got all those fragments, you wanna move everything and push
Yeah.
them all to the left, and then you have all that space on the right. So given a system that performs compaction, reading or writing a word, which is 32 bits. Which is 4 bytes, takes 10 nanoseconds. How long will it take to compact 128 megabytes of memory? What do you say?
I mean, that depends.
That's all the information you need.
At most, you have to.
I mean, how much stuff is currently on there?
It does kind of matter, right?
Is
Well,
it
like,
mostly
that's the
full or
amount- no,
mostly
yeah.
empty?
We're not given the size of the memory. We know the occupied memory is 128. The amount of memory, we have a system of billion gigabytes. But 128 needs to be compacted.
Okay.
So 128 is 1 to the 7, sorry, 2 to the 7?
And
Yeah.
2 to this, 2 to the
Yeah,
7,
2 to the-
227.
I don't care, whatever it is, tell me the end. How would you work out the end? Work out the answer. Work it out on paper or work it out yourself.
And it's, yeah.
How long will
for
it
each-
take? It's
For
very
each one,
easy.
you have to read and write, or read and write. That's.
Make the necessary assumptions that you think you have to make, and we'll see if you're right. Tell me the number. I want the number, both of you. Yeah, you can write it out. Yes.
Give me a second.
Well, it's, hang on.
Yeah. And
320 nanoseconds?
no,
Show me your work.
Well, 4-bit, if you have 128 megabits, so it's. Hang on. I don't know.
4 bytes, why is it bits?
Bytes, yeah,
We have 4 bytes, and we have
so that's
to,
32.
4 bytes takes 10,
32,000
and we have 128 megabytes.
Yeah, megabits.
So we're gonna have,
128.
128 million
100.
byte.
here, where do I have my marker?
No,
Yes.
it's
128
It's gonna be
so
32 million bucks.
It's gonna be 120
nanoseconds.
8
320 million.
times,
32
wait,
seconds.
time, what is it?
64
2 to the 20th
It's 60.
divided by 4.
So it's
So it'll be 32 times 2 to the 20th units, that's how many times
Yeah.
we have to take 10 nanoseconds. Times 10 nanoseconds. That's the amount, that's the answer, that's,
times 2.
and that, but we have to do exactly times 2, because when we compact, we gotta read it and then write it. So it's times
Oh,
2
32 seconds, right?
and 32
So it's not-
and this number, that is the answer.
64 seconds.
So
Wait,
it's what? It's 64
seconds.
times 2 to the 20th nanoseconds. Now nanoseconds is, if we want to, convert it
10
to seconds,
nanoseconds.
What?
It's 10 nanoseconds.
Yeah, nanosecond.
times 10 nanoseconds.
Yeah.
So
Oh, sorry, that's.
this is hard because we have different bases.
640 seconds.
What?
Oh, no, it's
You have to multiply,
Yeah.
well, what is that number?
And 64 is 2 to the.
2 to 20 is about a million.
Wait, so let's take this, it's 6.4, it's 6.4 times 2 to the
It's
20th.
6 point, it's just 60.
Oh, not 64, it's 640.
What?
Yeah, 640.
640 times 2 to the 20th nanoseconds.
Yeah, and now 600, 2 to the 20 is about a million.
It's 10 times 64 is
Yeah,
600.
I know, but like. Here just put 64 as 2 to the 6, and just have 2 to the, and just have it as 2 to the 26 times
It doesn't matter.
seconds.
Okay,
This is fine, this is fine,
this is 2 to the 6, right? So I could change this to
2 to the
you don't have-
26,
26 and change this
and just.
to
get rid of
10.
it.
This doesn't make it easy.
But I still want to, if I want it, now you're trying to convert it from nanosecond to second.
We have 640 times 2 to the 20 nanoseconds, and 2 to the 20 is about a million, and a nanosecond is about, wait, what, how much is a nanosecond? It was a
Is it a
million?
billionth of a second?
A billion to the
Okay,
second.
fine, so that's 640 milliseconds. Is 640 basically
You gotta
million.
divide this,
640 million nanoseconds, just 600 nanoseconds, 640 million nanoseconds, which is.
What do you, oh, right, for,
that's the number of seconds.
So it's
That's the number of
2
seconds.
to the 2 to 26.
If you have a calculator, you can calculate it.
Like,
So we can, you're saying, let's approximate,
so just,
you wanna approximate, so
So
let's
then-
approximate and let's call this.
when you're just.
Wait,
going
wait,
to put us
Let's,
10 to the 8.
wait a second. Let's approximate, I'm going slow here. Approximately equals to, well, we can change this to, let's change it back to the way we had it.
Yeah.
640 times 2 to the 20th. And we'll divide this by 10 to the 9th, well, that equals. And that is an easy way to look at it, and then that's approximately equal to, well, we can knock off this, we change this to 3. And change this to 1, change this to 0,
Wow.
to the 20th. We'll change that to 0. Because this is approximately a million. And that's and we just took off a million, so the millions
Ah.
cancels. So now we got 64 divided by 1,000.
640 milliseconds.
What
This is
is,
seconds.
well, seconds equals. What are you talking about?
This is about-
It's 0.64 seconds,
640 milliseconds.
or equals, right,
Whatever.
what do you say, 64,
640 milliseconds.
640
Yes.
milliseconds, but if we wanted it in seconds, that would be the answer.
No, that'd be.
That would be the approximate answer.
No,
If you
that-
want the exact answer, you have to use a calculator.
Let me see it.
640 milliseconds would be 6.4 seconds.
So
Oh, yeah,
answer, what do we get? Here, he got 67
No,
seconds.
or 100.
No. 1,000.
Wait, he did it differently?
It's 1,000.
Oh, huh.
32 bytes.
No, alright.
No, he did the same thing that we did. He did the same thing that we did. He just did that weird.
Right.
Got a slightly different answer because he used a calculator.
So here's the calculator. Do you get the same answer? Yeah?
Yeah, he got 0.67.
Yeah, okay. 5. How much more time? We have 5 minutes. Okay, we can do it. All right. Where are we?
Performing a page request. Up,
Yeah, this one, by the way, yeah, okay, this one. I gotta change that. For example, where are we?
no, we're up there.
Yeah,
Yeah, that was the answer, but yeah.
performing a page request, page fault rate. Now, if you remember, we had, this is a little bit confusing, because we saw 2 numbers, we saw. Alpha, when we talked about the hit rate.
Yeah.
And now we're talking about the page fault rate, which is the inverse,
Yeah.
it's a P, but it's not really the inverse, that's the hit rate regarding the regarding different questions regarding the TLB. Here, we're talking about something else, we're talking about whether what is a page fault rate?
It's when
It's nothing to do with it's nothing to do with cache.
when you have to bring it in from memory.
Right, we need to read it from the disk. It's not that, we talked about epsilon, when we talked about alpha and epsilon, we were talking about whether we could get it in the cache. Or get it, or have to go to memory. Here, we're talking a different question. Can we get it in memory, or do we have to go to the disk and bring it in? Different question, and we use different letters therefore. It confused me, because when I looked at it, I said, why is he using P, let him use alpha? And then I remember that it's right. So P is, and it's also the inverse, P is the fault rate.
Yeah.
Okay.
That doesn't have to be, that's unnecessary.
Well, no, when pages we talk, right, you're right. Yeah, so that's the way it is though, that's the way it is in the book. That's the way it is in the textbook. Alright, effective access time. We will ignore the time used in accessing the page table. Oh, see what I'm saying? That's a very important point. We will ignore the time used in accessing the page table. We're not talking about the whole
Yeah.
question of, is it, whatever, we're not talking about page tables. We're talking about, is the memory there? So the effective access time is the hit rate times the memory access time In other words, how much time it takes me to get the memory. I got a hit. Now all I have to do is go get the memory. We're not thinking about the page table actually at all.
Mhm.
We're just thinking, because we're talking about different topic here. We're not talking about paging, we're talking about swapping.
Yeah.
And now that's the hit rate. And now the fault rate, well, I don't find it in memory. What do I gotta do? I still gotta access memory. I also gotta select the victim, swap a page out. Why did I write if necessary?
Cause if it's a hit, you don't need. to.
Because if it's clean, you don't need to swap it out. Swap a page in,
Maybe.
restart overhead. Now, for example, given, anything not given is assumed to be zero. So as if there's no information given on something, assume it's zero.
Mhm.
So memory access time is zero time. in other words. Memory access time is 1 microsecond. So that's this memory access time here is 1.
Mhm.
50% of the time the page being replaced has been modified and needs to be written to memory. So we got a 50% dirty rate,
Yeah.
if you want to call it like that. Page writing time is 10 milliseconds. Or 10,000 microseconds. Page writing time.
Yeah.
In other words, to write the page is I'm gonna have to write the page from memory, from the disk into the memory, or from the memory into the disk. Either way, it's gonna take me 10,000 microseconds or 10 milliseconds. It's a long time, right? 10 milliseconds. Okay. So what is the EAT? So here it is. EAT is what is 1 minus P? That's the
The chance that it's in main memory.
where P is fault. So this is that it's not a fault. If it's not a fault, it's just times 1.
One
Because its memory access is 1, and we're in the world of microseconds. All of our units are gonna be microseconds. So we're gonna use this microseconds 10,000. So we're in microseconds. It's very important to get your units consistent. So 1 microsecond times the hit rate. And now the fault rate, I have to go to disk, so it's gonna be 1 still, I still have the 1.
Mhm.
Plus 5,000 microseconds. Why 5,000? Because. Oh, did I divide this too many times?
What is the 5,000? There's no 5,000. There's a 10,000.
Oh. Page writing time equals. Yeah, why did
A victim selection time.
swapping a page out? What did I write here? Oh, I page writing time.
I guess with 50% chance it needs to be swapped out, so it's.
So,
The-
no, that's
Divided by 2.
No, I did it twice. It's my mistake. It's my mistake. I gotta fix this also. Sorry. I was doing this too quickly. I did it twice. I took this 10,000 and I said, oh, that I have to divide it by in half. And then I divided it in half again. So it should be like, this
One
would be
plus
10,000. This should be 1 plus 10,000 plus a half times 10,000. In other words, half of the time I gotta do. I gotta do 1 right. And all the time I have to do 1 right.
Yeah,
All the time I have to do 1 right. And half the time I gotta do an additional right. So you get some solution which is wrong here, but I can just change this to 5,000 instead of 10,000. That would be right. Change this to 10 from 5,000 to 10,000 to 5,000, and this all makes sense.
Yeah.
Then this would be the amount of time it takes, which is 1 plus 7,500 P. Well, P is the fault rate. So EAT, effective access time, is directly proportional, spelled wrong, to page fault rate.
that makes sense.
Right. The more you have page faults, the more time it takes to get data. All right, we'll stop there.
Alright,
Try to remember that we're at paging,
Sure.
and I gotta rewrite the slide a little bit. Give me- All right. 2 mistakes. I gotta change it to 42. I gotta change this to 5,000.
Yeah.